In this video, we're going to discuss equilibrium, or more specifically, it's called dynamic equilibrium between the reactants and the products. But before we do that, the last video we talked about was about collisions, and that's how you get a chemical reaction. So remember the two things you need to know in order to have a chemical reaction occur. When the molecules hit, they have to have proper orientation, and they have to have enough activation energy to break the old bonds. Once that occurs, then the product is starting to form and you have a chemical reaction. So what I'm going to do is I'm going to give you the rules about dynamic equilibrium first, and then we'll discuss what they mean. Okay? What this says is if we have the reactants and we have the products. So when a system is at dynamic equilibrium, the rate of the forward reaction, in other words, making the products, is equal to the rate of the reverse reaction, which means the products are breaking down, making the reactants. Now, it doesn't make sense to you now, but it will. Also, I'm going to give you the rules in order to have dynamic equilibrium. So the first rule in order to have dynamic equilibrium between the reactants and the products is you have to have a closed system. In other words, you can't gain any products or reactants and you can't lose any products or reactants. It has to be closed. That's the first thing. If you have an open system, you can't have equilibrium occur. Okay? Now, the other thing you have to have is this. Once the reaction starts making the products, in other words, when you have the collisions between atoms and molecules and the reactants start forming products, it keeps on forming products until the reaction can't hold any more products. That means if the products are saturated, then it can't hold any more products. So that's the second rule. So you got to have a closed system and the products have to be saturated. So, closed system, products saturated. Now, other rules. So the third little rule is the ratio between the reactants and the products must remain the same or be constant. Okay, we'll discuss that later on. Right now, these three rules don't mean anything until we start going over examples of equilibrium. And the one very important thing, number 4, you know, when you hear equilibrium, most of my students say, oh, it's an equal amount of reactants and an equal amount of products. That's not it. Okay, so now, basically 4 rules for a system at dynamic equilibrium. You have to have a closed system. You can't gain or lose any concentration of reactants or products. Once the products are starting to be made, then the reaction fills up with products. That's called saturation. So the 2 rules, you got to have a closed system and the products have to be saturated. Once that occurs, now you can have the rate of the forward reaction, making the products, equals the rate of the reverse reaction, the products breaking up, making reactants. Okay? Almost never equal concentrations, so that's not what equilibrium means. And also, if whatever I do on one side, if I double the amount of reactants, then the products double. So you have to have the same ratio. Always the same ratio. Okay? All right. Now, there are three types of equilibria. Okay? Equilibria is the plural for equilibrium. There's 3 types. And the first type we're going to go over is called phase equilibrium. So here are 2 examples of phase equilibrium. All right, the first example is phase equilibrium between freezing and melting. So 0 degrees, if it freezes, it turns into a solid, and if it melts, it turns into a liquid. So at 0 degrees, you have a phase equilibrium. At 100 degrees, you also have a phase equilibrium between boiling and condensing, which means it's between a gas and a liquid. Okay? So let's just take the first one. Everybody's done the first one and seen it, even though you don't know that it was actually a phase equilibrium. It's a super hot day. You're sitting on your porch. You just exercised, and you get a glass of water. You put a ton of ice in it, and you're drinking that water. You're drinking, and there's a little bit of water left in the bottom and you have all the ice cubes on top. And you shake that to get that water out, shake it a little bit more, and all the ice cubes come down and hit you in the face at the same time. And you look, and all the ice cubes are frozen together. So that little space between the ice cubes is like a phase equilibrium between liquid and solid, because it's continually freezing and melting, freezing and melting. So that would be a phase equilibrium that everybody has happened probably. Now, here's another example. So let's pretend this is a glass of water. So you have a glass of water, there's H2O liquid, and there's H2O gas above. So what's going on is this. At that glass of water, the liquid is evaporating into gas. So the reaction is going that way, all right? And the gas is escaping. So remember our rules. If it's not a closed system, you can never, ever, ever have equilibrium. Well, this is an open system, because as the water liquid evaporates to gas, it's given off into the atmosphere. So what we have to do is this. We have to close the top. So once we close the top, like put saran wrap on top or put a stopper on it or anything like that, once we close the top, the reaction keeps on going this way. So the liquid water is still evaporating to the gas water or the water vapor, and it will keep on going this way until the second rule is established. In other words, it keeps on going and evaporating until this whole area above the water is totally filled with water vapor. Once it's filled with water vapor, the two rules have been met. Closed system and the products are saturated. Once that occurs, then and only then can the reaction fire backwards. And now the reaction is at equilibrium. Notice there's a ton more water than there is water vapor. So the reactant and the products don't have equal concentrations, but closed system, products are saturated. And what you will see is you will start to see little drops of water forming on the bottom of the saran wrap. Little drops of water. And what's going to happen is, as the water evaporates and forms these drops, the drops will drop back down. And it will continue going like that. That is called equilibrium. So, closed system and the products have to be saturated. In this case, the water above, in this case, the air above the water is saturated with water vapor. Then you can have equilibrium occur. That's the best example of phase equilibrium. So the rules one more time for this. We have a closed system because we put saran wrap on top of the glass of water. The air above the water is saturated with water vapor. So once we have the air above the water saturated with water vapor, it looks like this. Look, H2O liquid is turning into H2O gas, but it's only going this way. Once the products are totally saturated, then the reaction can go backwards. And what that means is, when you see the arrows going both ways, you know that this reaction is at equilibrium. Okay? So, we're at equilibrium right now. That's the first type of equilibrium. The next type of equilibrium is called solution equilibrium. Now, this reaction is going to be called solution equilibrium. Now, before we do it on the board, remember what a solution is. A solution is a homogeneous mixture. which has a solute and a solvent. And a homogeneous mixture, such as, we're going to do this one, salt water, it all means that you can't filter it because there's no layer on the bottom. It's all dissolved in there. So watch what we're going to do. We have a glass of water, and you know that if it doesn't have a top on it, then the liquid water is escaping and making water vapor, but there's no top on it. So this reaction can't be at equilibrium because it's not a closed system. Now, we're going to take solid salt and we're going to dump it in the water. Now, if you remember, solid salt, when you put it in water, breaks up into positive and negative ions. Now, the reaction is going to go this way. So the reaction is going from NaCl solid, we're dumping it in water, and it's dissolving, and it's dissolving, and it's dissolving. But there's a point where this water can't hold any more ions. And how do you know when that point is reached? When you see a little bit of salt on the bottom. Once you see that salt that's on the bottom that's not dissolved, that means that that water is holding all the salt it can hold. So what that means is it has fulfilled the second rule, which means the products are saturated. So that water is totally saturated with Na plus and Cl minus ions because there's a little bit of NaCl at the bottom. Now what about the first rule, closed system? Well, we know that the water is turning into water vapor, and that's not the closed system, but here, in here, the salt can't jump out of the water. So this really is a closed system for this. So once all the water can hold all the salt it can possibly hold, then this reaction can reverse itself. So now, as an NaCl solid dissolves, what that means is one Na plus and one Cl minus ions crystallize. Okay? So in other words, as the Na and Cl form solid salt, then one will dissolve. So we have a closed system, products are saturated, and here's what's going on. The rate of dissolving this is a big one, but now what's happening, the rate of dissolving equals the rate of recrystallization. All right, so this is called a solution equilibrium, when the rate of dissolving equals the rate of recrystallization. Okay, those are two, but the major one is the one that's coming up, and that's chemical equilibrium. So a little bit of review. There are three types of equilibria. Phase equilibrium, which we went through, solution equilibrium, which we went through, and now the most important one of all, chemical equilibrium. Now, that's important, but once again, I told you you're going to hear the rules over and over and over again. In order for a system to be at equilibrium, the system has to be closed. In other words, reactants can't come in and products can't go out. So it has to be a closed system, and it has to be totally filled with products, totally saturated with products in order for the equilibrium to occur. And once again, don't forget, equilibrium does not mean that the concentration of the reactants and the concentration of the products are equal. That's not what it means. It means the rate of the forward reaction equals the rate of the reverse reaction. That's what it means. So before we go into chemical equilibrium, I have to give you something called Le Chatelier's principle. So this is Le Chatelier's principle. And it's like a life principle, actually, not just for chemical reactions. Le Chatelier's principle. When a stress is placed on a system at equilibrium, the system will react in such a way as to remove or release the stress. So what the heck does that mean? Okay, so you're walking along a path in a forest, you're at equilibrium, you're loving life, loving nature, and there's a rattlesnake right on the path. So that's a stress on your system. You don't walk over and pet it. You wait, it slithers away, the stress is gone, and you continue on. All right? Now, same thing with you're at home with your parents, everything's cool, and then all of a sudden something happens, you have a big fight with your parents. That's a stress put on your system. And you run out the house, all right, to remove or release the stress. Well, you're not going to run away forever, maybe an hour or two, then you come back and then everything's back to normal. So, for a chemical reaction, it's the same principle. If you put a stress like add concentration or more surface area or heat or pressure or anything like that on a system at equilibrium, it'll react in such a way as to try to remove the stress, but then it'll go back to equilibrium. And that's what we're going to do with these chemical reactions that are at equilibrium. So let me explain what's happening again with my students. All my students, which would be X plus Y, that's boys plus girls, are in the hallway. All the doors and windows are shut except my door. So it's a closed system, okay? But they haven't started to react yet. Once I put them all in the hallway, they start bumping into each other, making proper collisions, and so it will be boy and girl. Now we start making product, which is X, Y. Now, once they make the product, they come into my room and they sit down. And it keeps on coming that way, all right, forward reaction, making product, until all the seats in my room are taken. Once all the seats in my room are taken, that means that my room is saturated with product. No more product can go in here. So what that means is, now, since it's a closed system and the products are saturated, the next group of product that come in have to replace another group that must go out. So now I go like this, and this reaction is at equilibrium because the products are saturated. So once another pair of students or molecules walk in, a pair has to leave. So that's what dynamic equilibrium is. Not equal amounts of concentration reacting product. So this is it for right here. And now if I opened a window up, that would make an open system. And what would happen is this. Once another product walks in and there's no seats, they get kicked out the window. And so the reaction will only go toward the products. It will not be in equilibrium anymore because there's an open system. So the products are escaping. So the reaction must go on to completion. It will never be equilibrium unless I shut the window again and make it a closed system. Okay, so now what's going on is this. We're going to do an analogy for a chemical reaction. We have A, our boys outside, B, our girls outside, okay? It's a closed system. All the doors are closed, all the windows are closed. But in this room, if you can take a peek, just pan around, in this room is where the products are going to be once they come through that door. So there's no products in here yet, so that means the reaction has not started. So let's go out and see where the A and B molecules, let's see what they're doing out here. Remember, they have to have proper collisions before they come in here and form products. Okay,
told me she was gonna hide from me.
Okay, here they go. We have A molecules and B molecules. They are going around. Some of them are colliding because they really don't know where they're going. So the minute that they collide and form a proper collision and enough activation energy to break the old bonds, they come through this doorway. This doorway is going to be the yield sign. Okay, proper collision, people? So now here come the products. As soon as they come through the door, they have collided perfectly. And now what they're going to do is they are going to start to try to saturate this room, which means the products will be saturated. So now if we pan around, we will find that every chair is taken, which means the products are totally saturated. So now if you look over here, what happened is A and B reactants came in and they formed AB. Now, this room is totally saturated with products, so what can happen now is the reverse reaction can happen. So now, if 2 extra molecules come in, 2 have to go out. Okay? Now that's what's going on. So what is equal in equilibrium? Not the amount of reactants and products. What's equal in equilibrium is the rate of the forward reaction must equal the rate of the reverse. So now, what would happen if we open the system? In other words, okay. If we open the system, that means if we open this window and I took 2 products and threw them out the window, would this reaction be at equilibrium? No, because it's an open system. So what that means is once the products are formed and come in this room, they'll be thrown out the window. So the reaction will continue on until all the reactants are used up and all the products are out the window. Everybody got it? Okay, here are my molecules. Good job, guys.